Hello everyone, hope you're having a good day. So today we would be discussing about the topic complex functions from complex analysis. But before going ahead with our main topic, let's try to understand what do functions mean in real analysis, or what do real functions mean. So a real function is a function which assigns a real number to a real number. They don't have anything to do with complex numbers. So it's like I plug in some real numbers into a real function, it would give me real numbers as output. But complex functions are a bit different from real functions. They assign complex numbers to complex numbers. And now what that means is that the input and output of a complex function are both complex numbers. See, suppose I have a complex function f of z. So now a complex function is a function whose input and output are both complex numbers. So the input, I would input some complex number, I would get a complex number as output. This is quite different from real functions. So now let's move ahead with our next topic, limit of a complex function. Before actually getting ahead with limit of a complex function, let's actually understand what do limit of a real function means. Now here I'm actually comparing the topics with real analysis so that you have a good picture of what is actually happening and what are the differences between the two. So before this, let's understand what limit of a real function means. So when I say that limit x tends to small e f of x equals to capital A, it means that as x gets closer and closer to A, the function gets closer and closer or approaches capital A. And here there are only two possible ways of approaching a point. Either it would be from left hand side or right hand side. So what I mean to say is that in limit of a real functions, there are only two possible ways for me to approach a certain point in the plane. Either it would be from the left hand side or the right hand side. But in complex things again turn out different. And now when we talk about limit of a complex function, the basic idea stays the same. We approach a certain point in the z plane, the function approaches a certain value in the omega plane. But the number of possible ways of approaching a certain point in the z-plane is where lies the difference. As there are infinite number of ways of approaching a point in a complex plane, yes, you heard it right, there are infinite ways. So the thing is that when I talk about a limit of a real function, I would have only two ways of approaching a point. It would be either from the left hand side or the right hand side. But when I talk about limit of a complex function, there would be infinite number of ways of approaching a certain point. So I would have actually to check all the ways, possible ways of approaching a point, and check whether limit exists and it's same for all the possible ways. So now let's actually try to understand a formal definition of the same. So you can see a definition on the screen. It says a function omega is equals to f of z is said to tend to a limit L as z approaches a point z naught. Now if for every real epsilon we can find a positive real delta such that mod of fz minus L is less than epsilon, for mod of z minus z naught is less than delta. Now what these lines actually mean is that here epsilon and delta are very small positive numbers. So the only thing which they mean is that as we get closer and closer to a certain point, fz gets closer and closer to some other point. And here those two points are fz gets closer and closer to the point L, and z gets closer and closer to the point z naught. So these lines means that as I get closer and closer to z naught, my function gets closer and closer to L. And this definition of limit, though similar to that in ordinary calculus, is quite different for in real calculus. X approaches x not only the line, whereas here z approaches z not from any direction in the z plane. That is what I actually said in the last slide, right? like we only have two possible ways of approaching a point in real analysis or a real line, but in complex things turn out different. There are infinite ways of approaching a point. So the basic idea is still the same. We are approaching a point, and my function is also approaching some point provided the limit exists. So the basic idea is still the same, but where lies the difference is the number of possible ways of approaching a certain point. And as you can see in this slide, that we have a figure 20.1, and it still says the same thing with which we discussed in the previous slide. See, the delta in the slide, as you can see in the figure 1, is actually a very small positive number, and the z is any point which we would be actually selecting. So now actually let's try to understand the stuff which I explained in the previous slide in a pictorial form. So as you can see, there are two figures. One is a z plane and one is omega plane. So z plane is actually the input plane and the omega is where the output reflects. So you can see a point z naught, which is actually the point we are approaching, and a delta, which is nothing but the distance between the point z and z naught, and z is any number, any point. Then that would actually depend on the way which I am approaching the point z naught. And this, and when you see the omega plane, you have epsilon, which is nothing but a very small positive number, and you have L, which is actually the point to which the function f of z would be approaching. So the thing is still the same. Like as I'm approaching a point z naught in the z plane, as I'm approaching it through any way possible, I would actually see that my function f of z would also approach a point, and that is L, as I approach the point z naught in the z plane. So the thing is that you can see that there are two circles drawn, and that these two circles actually represent that there are infinite number of ways of approaching a point. And like the reason behind is that this is a two-dimensional stuff. All this is happening in two dimensions, so I can approach in any ways. But in real analysis, we only had either two possible ways: either it would be from the left or from the right. But things in complex are different. So now let's actually try to understand what continuity of a complex function means. So before actually getting into continuity of a complex function, let's understand what does continuity of real function mean. See, suppose I have a function f of x, and I want to know that whether this function is continuous or not at a certain point a. So what I would do is I would actually use limits to find whether that function is continuous at a particular point a. So what I would do is, like, I would actually apply limits, like limit x tends to a f of x, and I would actually check if the value of these limit and the value of the function f of x at the point a are same. If they are same, then this function would be called continuous. And now the idea is still the same in even in complex numbers. I would do the same thing what I did in real analysis to check the continuity of a complex function. It's just that now we are dealing with complex numbers. So see, suppose I have a function fz. Now a function f of z is said to be continuous at z is equals to z naught if limit z tends to z naught f of z is equals to f of z naught. That is what I said, right? The value of the function at that point and the limit value of the function at that point, if they are equal, then the function is said to be continuous. Now let's actually move ahead with our next topic of derivative of a complex number. Before actually going ahead with derivative of a complex number, let's understand what derivatives mean in real analysis. The idea would still stay the same, but there would be some differences between the two. So the derivative represents the rate of change of a function at a given point of a real function. So it's like derivative basically represent a rate of change of a function with respect to any parameter we would choose. And now the basic idea still is the same. The derivative of a complex function at a point provides the rate of change of the function with respect to a complex variable. So the first difference is that there we were telling the rates with respect to real variables, and here it is complex variables. A key difference is that complex derivative involve considering limits from all directions, not just from left and right as we do with real functions. So that is what we have been discussing since the start. It's like we only have two possible ways of approaching a certain point in the real analysis, but in complex we have many number of ways of infinite number of ways of approaching a certain point. So actually, let's try to understand the formal definition of the same through the slides. So what the slide says is that let omega is equals to f of z. By the way, the function fz is actually represented by omega. You could also call it as w. Be a single valued function of the variable z is equals to x plus iy. Here z is our complex variable. Then the derivative omega is equals to f of z is said to be defined if d omega by dz is equals to f dash of z, and the limit has to exist, like limit delta z tends to 0. And this is basically the limit definition which we studied in real analysis. It is almost similar, except the fact that here we are dealing with complex variables and complex numbers. Provided that the limit exists and has the same value for all the different ways in which delta z approaches 0. That is what we discussed right now, just now, right? Like, if the limit which I'm actually applying to my complex function has to exist and has to have the same value for all different ways in which delta z approaches 0. It should not be like for certain number of ways I get a certain value of the limit, and for other ways I get a different value. Then it is that doesn't work. Then the limit would not exist. So for all the possible ways of approaching a point, I need the limit to exist for me in order to define a derivative. So in order for me to define a derivative, the limit has to exist. So let's actually go ahead with our next slide, which says that say suppose a p of z is fixed and q of z plus delta z is a neighboring point. You can actually look into the below figure. The point q may approach p along any straight or curved path in the given region. That is, delta z may tend to 0 in any manner, and delta w by delta z may not exist. It therefore becomes a fundamental problem to determine the necessary and sufficient condition for delta w by delta z to exist. The fact is settled by the following theorem. Okay, so what these lines mean is that, say, suppose I have a point on a plane, xy plane, and that is like p of x comma y is a point, and q of x plus delta x comma y plus delta y is another point. I can actually, this is the same was actually mentioned in the first line. Q of z plus delta z, it can also be written as q of x plus delta x comma y plus delta y. So that is what is the lines actually mean. So that is what we have been discussing, right? There are many different ways. So I can actually go from p to q along a straight line, or I can choose any curved path. Now there are infinite curved paths which are possible to reach the point q. So it also becomes necessary for us to actually build up some conditions which are necessary and sufficient for me to define whether the derivative will exist or not. So in the next slide, we actually talk about Cauchy-Riemann equations. So these are the equations which are actually very useful for me to actually determine whether the derivative would exist or not. I cannot actually, like approach in all the possible ways, infinite ways, and uh, find out whether the limit value is same for all. It's not possible, right? It's not practical. So we have to find some alternative to doing that crazy stuff. so here here Cauchy-Riemann equations are for RSQ. So let's say suppose these condition like Cauchy-Riemann equations are necessary. Let's prove this that this CR equation is necessary for the derivative to exist. So say suppose if fz possesses a unique derivative at z naught, I am actually assuming that fz has a derivative at a point p of z, then I can actually write f of z equals to limit delta z tends to 0. And this is actually the basic limit definition. There is nothing much difficult difficult stuff to understand. So so delta z tends to 0, so I can actually write the same thing like limit delta x tends to 0 and delta y tends to 0. And this entire thing, this entire first term is nothing but the f of z plus delta z. Here we are actually defining a function fz, which is actually something like u plus iv, where u and v are functions of x and y. So see, and this second term is nothing but f of z, which we actually defined, right? And the denominator is nothing. They have just written z is equals to x plus iy, and they've written delta z equals to delta x plus delta y. Still delta z can approach 0 in any manner. We can first assume delta z to be wholly real and then wholly imaginary. So when delta z is wholly real, then delta y is 0 and delta z is equals to delta x. So this line which I actually read says us that now delta z can approach 0 in infinite number of ways. We just saw in the previous slide. So what we do is we first assume delta z to be wholly real and then wholly imaginary. Here what I'm doing is that I'm actually standardizing the things. So first I will, if I approach delta z only in say suppose v1 and they then approach v2. So for derivative to exist, both the limit values should be equal, right? So I'm actually trying to make some conditions and trying to derive some statements. So at the end, I would equate those two and actually get some conditions which would be necessary. So when delta z is wholly real, then delta y is 0 because delta y is nothing but the imaginary part, and then delta z would just condense into delta x. So now the next step says us the same thing. Wherever you have delta x, you would just write delta z, you will just write delta z, and wherever you have delta y, you would just write 0. So it's like delta z tends to 0, limit u of x plus delta x comma y. Here delta y becomes 0, and wherever you find delta y, you will just substitute 0. So now if you actually see this entire equation, what you would see is that if I actually bring out this u terms together and v terms together, I would actually find that this is nothing but equal to del u by del x plus I del u by del x. So it turns out that this turn out to be partial derivatives, right? The reason behind getting partial derivative is that my z is not actually a function which is only depending on one variable. It is a function which would actually depend on two variables. So their derivatives would actually be partial derivatives, not just simple or ordinary derivatives. So now my second condition would be like when delta z is wholly imaginary, delta x would be 0, because if it is wholly imaginary, the real part would be 0. So my delta z would just be I delta y or iota. You can also call it as iota. So fz, in fact f dash of z would be limit delta y tends to 0 u of x comma y plus delta y. So wherever you have delta x, you would just substitute as 0, and this entire equation would just turn out to be 1 by iota into del u by del y and this stuff. So this would be equal to del u by del y minus I del u by del y. So this simplification is nothing but I've actually multiplied and divided iota in this first term. So this would actually end up getting this equation. So now the existence of fz requires the equality of 1 and 2. The reason behind saying this is that because whatever way I approach a certain point, the limit value has to be equal for the derivative to be equal. So if the limit values are equal, that is when I actually get the derivatives equal. Here we are actually standardizing the things. So when I tell that these two are equal, that is when I can talk about the existence of a derivative of a complex function. Now in the next slide, you can actually see that I've actually equated these 2 points, the equation 1 and 2. So when I actually equate, so these are nothing but you could actually equate the real and the imaginary parts from both sides, since these are somewhat like complex numbers, right? So when I actually equate the real and imaginary parts, what I get is del u by del x equals to del v by del y, and del u by del y equals to negative of del v by del x. Thus, the necessary condition for the existence of the derivative of f of z is that the CR equation should be satisfied. That is what I told, right? Like, see, suppose if the limit values were different, then these conditions would not have been satisfied. So for I have to get something whether these conditions are satisfied for the limit to exist. So it's like if the limits are seen, then these conditions have to be satisfied, and that is when I can actually talk about derivatives. So these are the necessary conditions. Now actually let's prove that these conditions are sufficient. I don't need anything extra for actually to check whether derivative exists or not. So let's actually go ahead with proving whether that these conditions are actually sufficient. Say suppose I have a function fz function possessing partial derivatives at each point of the region and the CR equations are satisfied. I am assuming that the complex function possesses partial derivatives at each point of the region and the CR equations are satisfied. I'm actually assuming this. So if I actually assume that the partial derivatives exist and the equations are satisfied, so now I can actually expand the given function using the Taylor's theorem, right? So our so we would be expanding this function using Taylor's theorem, and I would be expanding the function f of z plus delta z. And I'm actually also, you could also see that while I'm expanded the function, I've actually used the theorem like Taylor's theorem for two variables. So after expanding, I'm actually omitting the powers beyond first powers of delta x and delta y. And the reason behind doing is that as delta z actually tends to zero, the higher powers would actually be very small numbers. So that does not make any much significance. So I'm actually omitting the powers of higher powers of delta x and delta y beyond 1. So what I would just end up getting is that f of z plus del u by del x plus I del v by del x into del x plus del u by del y plus I del v by del y into delta y. So you can actually work this thing out. It's not of like something like very difficult. You just have to use the theorem for function of two variables. Now what I would do is I would end up and also I'm actually subtracting f of z on both sides of the equation. So I would end up getting the equation, this equation, f of z plus delta z minus f of z equals to del u by del x. Now using the CR equation, I would actually replace these two terms, del u by del y and del v by del y, using CR equation. So after actually replacing and simplifying all these stuff, this is only a simplification process, I would actually end up getting the limit definition. I mean, after actually simplifying, then you have to apply the limit to this function. So you would actually end up getting the same del u by del x plus I del v by del x. So what is this? What this essentially means is that I'm actually taking a function and expanding it using Taylor's theorem, and I'm end up being getting a limit definition, something, and also a derivative in fact. So this actually proves that the CR equations are sufficient, necessary and sufficient conditions for a derivative to exist. So this actually proves. You could actually work out on this simplification stuff. I have not gone in detail. Even in this slide and the previous slide, these are very basic simplifications. So next, actually, let's move ahead with our next topic, that is analytic function. So a function which is single valued and possesses a unique derivative with respect to set at all points of a region R is called an analytic function of z in that region. So what the line means is that if there is a function and it possesses unique derivative at all points of a given region, it is an analytic function. An analytic function is also called a regular function or an holomorphic function. So these two are actually the alternative names of analytic function. It can also be called a regular function or a holomorphic function. So say suppose if u and v are real single valued functions of x and y such that the partial derivatives are continuous throughout a region R, then the Cauchy-Riemann equations are both necessary and sufficient conditions for the function fz to be analytic. So what we just understood is that if there is a function which has unique derivatives at all points of a given region, then it is an analytic function. So how do I actually know if I am given a function, any complex function, if I'm asked to actually know whether it is a analytic function or not? What I would do is that I would actually check with CR equations, like whether the Cauchy-Riemann equations are satisfied, or and also check whether the partial derivatives of the real and imaginary part of the complex functions are actually continuous. The u here, u and v are actually the real and the imaginary parts of a complex function, and these two conditions, actually the partial derivatives and the Cauchy-Riemann equations, these are actually sufficient and necessary condition for a function to be analytic. And the real and imaginary parts of the analytic function are called conjugate functions. The relationship between two conjugate is given by CR equation. Okay, so what this line means is that the real and the imaginary parts of an analytic function are called conjugate functions. It's like u and v are actually the conjugate functions of an analytic function. So it's what it essentially means is that you have a function, and if it possesses derivatives at all points, it is analytic. And so if you have to check for analyticity of a function, complex function, you would actually have to get Cauchy-Riemann equation satisfied and also check whether the partial derivatives are continuous throughout a region R. So that is what actually is R and is the necessary and sufficient condition for a function to be analytic. So this comes with this we come to an end of our today's topic. So let's actually meet in the next video. Till then, stay tuned. If you have any doubts, please let me know in the comment section. If you're looking for the slides, you would find the PDF of the slides in the description. Do let me know your thoughts about this video, and let's see meet again in the next video.